What is a covalent bond? It's a shared pair of electrons. Now, there are many types of covalent bonds. You can have a triple bond, a double bond, a single bond, or a dative bond where both the elements in the shared pair of both the electrons in the shared pair of electrons come from the same element. And the actual covalent bond itself is the electrostatic attraction between the shared pair of electrons and the positive nuclei of the atoms in question. Giant covalent bonding. A diamond, an example of a giant covalent structure. All its carbon atoms bonded 4 times. There are no delocalized electrons, and there are no ions, so it's completely unable to carry any kind of charge, as are all ionic structures, giant ionic structures, apart from graphite, which is an exception as it has a sea of delocalized electrons which are able to move through the metal between its carbon structures, and therefore it is able to carry charge. But as I say, it's the exception. No other giant ionic structures can do this. Solubility. No giant covalent structures are able to soluble in water, as the covalent bonds themselves are too strong to be broken by water molecules. The strength of the bond is very strong and requires a lot of energy to break, so hence both graphite and diamond and all other giant covalent structures have very high boiling points and melting points, whatever you want to call it. Simple covalent bonding. Now, simple covalent bonding is the same as covalent bonding in the sense that all it is this shared pair of electrons, but in between the molecules, the intermolecular forces, they're very weak, the things holding the molecules together. These are hydrogen bonds, dipole-dipole forces, and London forces. These, as I say, are extremely weak compared to the other bonding, ionic and covalent and what's not. So these are very easily broken with very little heat, giving them a very low melting point and boiling point. The solubility, no covalent substances are soluble, as the covalent bonds themselves are too strong to be broken by water molecules. And when it comes to conductivity, again, not at all, because there's no delocalized electrons and there's no ions present to carry charge, and it's as simple as that. It's a shared pair of electrons. It's a shared pair of electrons. 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 What is a shared pair of electrons? Oh my god!
Non-metals and metals that bond ionically make giant ionic lattices. This is done by the metal losing electrons and the non-metal gaining some. This leaves a positive metal and negative non-metal ion, and because opposite charges attract, an electrostatic attraction is present between them which causes them to be pulled together. The oppositely charged ions are formed in a regular way that form giant ionic lattices. The electrostatic between them is strong, which means that they require a lot of force to break up the lattice. Therefore, ionic compounds have high boiling and melting points. When in a solid state, ionic compounds are unable to conduct electricity. This is because the ions are unable to move and are fixed. They therefore cannot be mobile carriers of charge. However, when the ions are in liquid or aqueous state, they are able to carry charge as they are able to move. Many ionic solids are soluble in water and other polar solvents, but not all ionic compounds will be. It depends on whether there is enough attraction between the solvent molecules and the ions to pull the lattice apart. Metals form giant metallic structures. Metals lose their electrons and they delocalize to become positive ions. There is a strong electrostatic attraction between the positive ions and the delocalized electrons. This is what causes the bond to be held together. These forces are strong, so it therefore requires a lot of energy to break, thus making the boiling and melting point of the giant metallic structures high. Metallic structures are good at conducting electricity. This is because the delocalized electrons are free to move and carry charge. Metals are also insoluble in all solvents because there is no attraction strong enough between the solvent ions and the electrons that could overcome the electrostatic force of the positive ions and the delocalized electrons.